Welcome back, everyone. This is the final lecture of the mini-series in training RLHF from scratch. In this lecture, we use the material we learned in lecture 1 and 2. Here is the overview of the lecture. We first review the key concepts. Secondly, we train a reward function. And finally, we will go over RLHF pipeline from scratch. So let's get to work. LLM training usually have two stages, pre-training and fine-tuning. In pre-training, which is the larger stage, the model is trained through autoregressive, aka next token prediction. So some tokens are given to the model, and the model is supposed to predict the next word in the sequence. Note that this whole process is done in one go in parallel and not recursively. This is extremely important in training LLMs, and this is done in mask self-attention of decoder transformer models. There are several notes here. This method allows for any kind of text to be used in self-supervised training. So training can be as large and as diverse as the whole internet. Secondly, I talked with many researchers in the field, including some of the initial developers of the method. And no one was expecting this method to work so well. So this is still a mystery. Thirdly, this is not truly a recursive method. While powerful, this might be the source of many surprises that we get from LLMs. In the future, do expect hybrid models that combine benefits of both transformers and RNN to emerge. A pre-trained LLM does not follow instructions. And it is expected because it has been trained to do next token prediction. However, there are several methods to tune the model to follow instructions and make the model much more useful. The first one is in-context learning. This is when you provide an appropriate prompt, usually showing how a task is done with several examples. And then ask the model to repeat the process for a new example. This is also called few-shot learning. Note that in this method, the weights of the model remain unchanged, so it does not need any training. This is a very helpful technique if you want to hack together a quick solution or if your problem only needs generic knowledge and reasoning. The second method is supervised fine-tuning, aka SFT. The training setup and task is very similar to pre-training, but here you collect a high-quality dataset that specifically focuses on the problem interesting to you. A variant of this method is called instruction fine-tuning, which divides the text into queries and responses. The model is given the queries and it is trained to provide the responses. This is a simple training setup and hence a popular method of doing fine-tuning. In this method, the focus is on the data set generation, and many recent projects focus on this direction. Examples are Alpaca, WizardLM, or Orca. The third method is reinforcement learning with human feedback, aka RLHF, which is the subject of this mini-series. Note that you can combine these methods. For example, GPT-4 is fine-tuned through RLHF, so it follows instructions, but you can still get better results if you give it some examples of what you want it to do. While SFT is simpler, recent articles showed that RLHF is superior from quality perspective. One common misconception is that RLHF is used only to make the model less harmful or unbiased or similar things, but RLHF is a general method of training and it can be used to train or fine-tune the model in a way interesting to you. Remember that this method was first developed to train robots to do tasks following humans. In the past few months, new alternatives to RLHF were introduced. Direct preference optimization from Stanford, reinforcement learning with AI feedback, and reinforcement self-training from researchers at Google. We will do a comprehensive comparison and we will publish the results soon. This is a very active and exciting area of research. At a high level, RLHF has two parts. In the first part, you train a reward function that captures the human preferences. In the second part, use the RL method and the reward function to align the LLM with the human preferences. Let's quickly review how the reward model is trained. Firstly, you collect a data set of prompts related to the problem interesting to you. Secondly, you create a response to the prompts using the LLM. This is usually done with a higher temperature so that you have responses that are diverse. Then you ask a group of labelers to rank the responses according to the preference criteria. For example, here, let's say that the prompt is how to get healthier. We give it to LLM and the LLM creates several responses. I don't know, eat a balanced diet, exercise, etc. The first human comes in and he or she ranks the second response to be the best response, and he or she also ranks the rest of the responses. The second human does the same, and so on and so forth. At the end, you will have overall rating for each of the responses. Note that some of the responses might get a tie. At the end, you sort all of the responses according to the overall score. At this point, your reward training data is ready. Now that we have the training data, the goal is to create a reward model that assigns higher score to the query responses that were preferred by humans. For example, we want the model to give higher score to the answer on the right. For training the reward model, we use a simple log sigmoid loss explained here. Consider a prompt X, which in this case is how to get healthier, and two responses, Y sub W for the winner response, which is eat a balanced diet, exercise, and get enough sleep, and Y sub L for the loser response. In this case, I don't know. We want the reward of the pair X and Y sub W to be higher than the score of the pair X and Y sub L. The loss defined here does exactly that. If the reward of the winner pair is higher than the reward of the losing pair, the term inside the sigmoid will be positive. Sigmoid of a positive number will be between half and 1. Log of such number will be a small negative number. With a negative sign in front, the whole term will be a small positive number. So the gradient will be very small and the model weights will not change much because the order was correct. On the other hand, with similar analysis, you can see that if the order is incorrect, the loss will be large and the model weights receive a large gradient to correct the order. In short, this loss will train a reward model that mimics the human preferences. Note that in the labeling phase, we create a rank over all the responses. But in the training phase, we compare only 2 of the responses at a time. The way it works is that depending on n, the number of responses, we will have n choose 2 pairs to use for each training step. So we always work with 2 responses at a time. Also, we ignore responses that have the same score. At the end of the training, we will have a reward model that captures the human preferences. There are several important notes about the reward model training. Firstly, the reward model architecture does not need to be the same as the main LLM of the PPO process. In fact, it is common to use a smaller model for the reward training since it can overfit sooner. Secondly, the basis of ranking can be as simple as a sentiment analysis or as complex as a feeling you have about a response and you can't even explain it. You will define what the ranking means, and as long as you are consistent, the reward model will learn to mimic that. Thirdly, you can use another teacher model, for example GPT-4, to do the ranking for you. This is the basis of RLHF approach. And lastly, it is very important to understand the power of creating a reward model. Currently, one of the main challenges in working with LLMs is the question of evaluation. There are general benchmarks such as MMLU, but people usually want to evaluate the model according to their own task. For this, you can train a reward model once and then use it as a benchmark for all the incoming unlabeled data and over all different models you have. So this is a very powerful and a scalable method for customized evaluation. Now, we have all the ingredients of an RL training. We have an agent, which is our LLM, and each action is the next token it generates. Also, we have a reward model to guide the LLM to create sequences aligned with our preference. Remember from lecture 1 and 2 that PPO training has 2 phases. In phase 1, the LLM creates a number of trajectories together with their required quantities. This is where the reward model is used. At the end of this phase, we put all these quantities into a data loader. In phase 2, we sample the data loader to train the model according to the PPO laws for several epochs. Then we go back to phase 1. As you remember, we use this method to train an RL agent to do a few games. Similar methodology can be applied to align an LLM with our preferred behavior. Now let's go to the implementation. Welcome back, everyone. Here, we're going to go over the implementation. We use InstructGPT paper closely to do the implementation here, but the implementation is pretty generic and it can be applied to other places. For example, the recent paper from Google DeepMind, reinforcement self-training. You can use the same reward mechanism that we train here to use it for that methodology. For the dataset, we use IMDb. The reason why we use IMDb is that it has just the right size for a tutorial. It's not too large or too small. Also, we use the axis of sentiment as the preference axis. The reason why that's a good thing for the toy example that we have here is that sentiment is something that as soon as you look at the paragraph that is generated by the model, you will be able to identify whether it's positive or negative. So after the training, the sentences that the model generates, you will be easily able to tell whether they are positive or negative, hence whether we did a good job of training the model or not. But the whole pipeline that we create here is very general. If you have the proper ranking of your own data set, you can use exactly the same training pipeline to align your model with your axis of preference. So let's go to the next cell. The requirements here are pretty generic. We use the transformer Hugging Face library to basically define the model architectures. You can define your own model architecture too, but for simplicity, we use just transformer. We use also the data set from Hugging Face to download IMDb data set. We need accelerate if you want to do sharding and you want to do it at a scale. Note that the whole pipeline is also scalable. You can do it on a machine with several GPUs or even several nodes, several machines. We write these libraries to a text file and then we install them here. You can comment these libraries out after the installation. Then we import the required libraries. Next, let's go to the settings section. Okay, next, let's go over the setting. After setting the seed, we use this model architecture, OPT 350 million. Note that it's a pretty small model, but it makes sense to use this small model. According to the original InstructGPT paper, the reward model has the tendency to overfit very quickly. So it makes sense to go with a smaller model. In fact, in their paper, while they were aligning the base LLM of 175 billion parameters, they were using only a 6 billion parameter model as the reward. So we follow the same idea here. Our reward model is going to be a lot smaller than the LLM that we align. The learning rate here is pretty sensitive. Just make sure that it's good for the model that you pick. Everything else is quite a standard. We use gradient accumulation to save us some memory. The sequence length here is should be compatible with the model and the tokenizer that you call. Here for us is 1024. Next, let's go over the data preparation section. For the data preparation, we have a very specific setup here. Because IMDb, since we're using sentiment, it's not formatted correctly for like the ranking that we use usually for reward training. So the preparation of the data is slightly specific and kind of weird. But I left a cell here that is more aligned with the common preparations for reward training. In fact, I'm using Anthropic RLHF data set here for preparation. I commented it out, but you can use this if you have a data set that you have already ranked. So here we use IMDb, and since we use sentiment, we have to do some particular preparation of the data, but nothing is complex here. If you go over it, hopefully you'll understand exactly how it's prepared. Okay, next, let's go over the model. Okay, now let's take a look at the model architecture. For the model architecture, what we need is a model that spits out scalars. Remember, we want to assign a reward to a paragraph of text. So to do that, we have two options. We can either get a pre-trained model from Hugging Face or a model that we trained some other place, and then do a transfer learning. On top of it, we put a linear head that spits out logits. An alternate method is that we use auto-model for sequence classification from Hugging Face. Note that this is in fact is created in Hugging Face for doing classification tasks on top of language models. But if we have just one node at the classification head, essentially it will speed out a scalar for us. So we can use that as the reward model. And in fact, it accepts most of the commonly used language models. Essentially, it puts those language models and adds a linear head on top of them. So I have a cell here that I commented out that I explain. Let me for a second bring it back on. That I explain how you can manually add a head on top of the language model that you have. So you can use, you can get a base model here. The base model can be any model, for example, from Hugging Face or the model that you defined yourself. And then what I do is that I get the last embeddings, and then I insert those embeddings to here. It's a two layer feed forward model. So it's a very simple linear head on top of feed forward neural net on top of the last embeddings that I have. Let me now comment it out again. Alternatively, what you can do is that, as I said, call this class with whatever model that you like. Most of the models from Hugging Face are supported here. And then you just need to specify the number of labels to be 1. Essentially, it spits out a scalar. There are also a few different things that you have to be careful about. So first of all, we use the torch type bfloat 16. So this saves us some memory without degrading the quality of the model much. Next is the device map. We use the device map auto. Note that if the accelerate library is installed in your machine, you can use device map auto, and what it does is that it automatically shards the model over the GPUs or CUDA cores that you have. This allows this pipeline to be completely scalable, in fact. But unfortunately, it is not supported for older versions of CUDA. And I believe that only from a CUDA 11 and on you can use it. And probably you also need the hardware to support it. But if it is supported, just use it. If not, comment it out. For a small model that we are dealing with here, you don't actually need sharding, but I left it here in case you wanted to use a larger model. Okay, let's go over training loop next. Next, let's take a look at the training loop. One can use the trainer function from Hugging Face. But if you do that, since the loss that we have is not one of the typical losses, you have to define a custom loss. It is explained in the trainer function at Hugging Face how to create a custom loss. But rather than doing that, I prefer to use the PyTorch default training loop, because in that way we see everything under the hood and nothing is mysterious to us. So let's take a look at the training loop here. For the optimizer, I'm using AdamW. You can use any of the other optimizers too. I believe that Adam or AdamW work very well. These are adaptive optimizers, work very well. So let's take a look at one of the batches and see how it works. I get a batch from the train loader. I look at the input IDs for the positive sample basically the winner and also the input IDs of the rejected sample. So then I give them to the reward model, and I store the logits that come out of them as the reward for the winner and the reward for the loser. If you remember from earlier in the lecture, we talked about these two quantities, and we know how to combine them to the loss. If you look at this expression here, this is the log sigmoid loss that we had in the lecture earlier. So we calculate the loss here. I then do some accumulation steps to save us some memory. I also do clipping of the gradient, because some of the times you get a huge gradient and it throws off the model out of the usual training. And that's it. I do a optimizer step, and that's it. The rest of the terms here are just for the progress bar and to show the loss along the training. After we're done with it, we can take a look at the losses over different epochs. In fact, we have only one epoch over different batches, and we see that the loss is going down. I haven't smoothed out the diagram here, but if you smooth it out, you see the elbow kind of shape that you like to see in the training. So that's the training of the model of the reward model. Next, let's take a look at the evaluation. This is some type of evaluation that is cooked for this specific example, but you might be able to do something similar to this for your own problem too. Just think about if your problem aligns well with what we have here. What I do is that I now look at the test set, so the values that the model has not seen before. And what I want to do is that I want to see what percentage of the time the model ordered them in the correct order. So the one with the positive sentiment is rewarded higher than the sample with the negative sentiment. That's the thing that I'm doing here. So I go over the test loader, I get the batches, I calculate the rewards, and I see what percentage of the time the reward of the winner is actually larger than the reward of the loser. So I look at the percentage and I print out the accuracy. Here you see that the accuracy is 0.98, which is an extremely high accuracy. But it is expected. Note that the sentiment analysis is a pretty simple task, especially for reviews of IMDb. So it's not surprising that the model can do very well in such a simple task. It is a transfer learning after all. The model already has seen a lot of language. So, and that's it. That's the reward training. I hope you enjoyed looking at the training loop here. And at the end, you can save the model and you can use it later for either benchmarking or for RLHF, which is the next step that we are going to go over. Welcome back. We are going to look at the final chapter of this mini-series, which is RLHF pipeline from scratch. Since we have gone over the theory and the details of all the steps in previous lectures, I'm not going to go over the explanations again. I'm going to mention the key concepts, but most of the steps I'm just going to skip the details. Please feel free to go back to the previous lectures to study those concepts in more detail. There will be a few new things that is specific to language models that I'm going to explain here, but the other parts I'm going to refer back to the previous lectures. So let's get to it. As always, the first few cells are for libraries and the installation of requirements. I have commented out the installation because my environment already has these libraries, but please, if this is the first time that you're running this code, make sure that all the libraries are installed. After the installation is done, we're going to import the required libraries and we're going to go to the setup section. Before we go over the setup, I thought that I have to explain why we're using OPT model, which is quite old at this point. Why we're not using a Falcon or Llama 2. The only reason is that I wanted to make the whole pipeline in a way that most of you can run it. And because of that, we needed to work with a model that is pretty small in size, but still creates decent text. So we could either go with GPT-2, which is even smaller than OPT 1.5 billion, but its quality was lacking even behind OPT. OPT seems to be one of the small 1.5 billion version of it, seems to be one of the smallest models that have decent quality. So that's why we're working with that. But the pipeline is not dependent on the model. It's agnostic to the model. So you can, if you have the resources and you do not run out of memory, you go ahead and use Llama 2 or Falcon or any other model that you like. Okay, let's take a look at the setup section here. So the first argument is the generator model path. This is a model that we train specifically to create reviews of IMDb type. What I did here is that I did a supervised fine-tuning of Facebook OPT 1.5 billion model on the training section of the IMDb dataset. Essentially, I did the next token prediction in a SFT fashion of that model so that it creates text that looks similar to the IMDb reviews. The next one is the reward model. This is the model that we trained at the beginning of this lecture. So we're just calling that over here. Sequence length 1024 should be something that is compatible with both of the models that we call here. Note that, as I explained before, the reward model and the generator model don't need to have the same architecture. And if you are dealing with different architectures, you just have to be careful that the sequence length should be the smaller of the two. The batch size is just the batch size of the data loader. The learning rate that I have over here is the best learning rate that I found for this setup that I have here. Note that the learning rate is very sensitive. So specifically for this RL setup that we have here. So if you deal with different type of models or different data, you probably have to do a little bit of hyperparameter tuning to find the best learning rate. Prompt size is the length of the prompt that is given to the generator to complete it. So 30 tokens, we will start with 30 tokens at the beginning and then the generator will complete it. Prompt batch size is the number of prompts that we create at each batch. Number of rollouts is essentially the number of completion that we do. These two are in fact very similar to each other. You could in fact go with just one hyperparameter. I separated them in order that if you want to work with them separately, you can have like different sizes. The number of epochs is the number of times that we create a rollout. So essentially the number of times that we go over phase one. Remember that we had two phases. The number of times that we go over phase one and we create a complete rollout That's the epochs that we have here. PPO epochs is that for each batch in the data loader, how many times we get gradient to update the model. So this is the hyperparameters for creations for the generator to create and complete the prompt. These are typical hyperparameters that are explained in Hugging Face data, Hugging Face webpage. So I'm going to skip the explanations of this. The only thing that matters is that the max new tokens, I left it at a smaller number. You can go with higher numbers too, but then it means that your memory is gonna be quite critical here. You might run out of memory. KL coefficient is something new that we haven't studied it before. I'm going to explain that in a bit in extended fashion. The rest of these parameters are the parameters that hyperparameters that we have seen before. In fact, even their values are exactly the same as what we did before in PPO training when we did some games through RL. So I'm going to refer to previous lectures to study the meaning of these hyperparameters. Okay, so let's go over the KL divergence coefficient. Okay, let's quickly go over the idea of KL divergence. Remember that the whole pipeline works roughly at a high level like this. We have prompts. The prompts are given to the generator model, and then the generator model generates responses to those prompts. The reward model looks at the responses, and if they are not good, it will punish the generator to create better responses, and so on and so forth. So we will go over this loop again and again. Now, this works, but the problem with this setup is that if we do that, something is very likely to happen, which in our RL world is called reward hacking. So basically, it will allow the generator to find a way to artificially increase the reward for the generation without the reward having a good quality. So for example, for us that we are looking at sentiment analysis, if we just go over this, it's not guaranteed that it happens, but it's very likely that the generator that you will get at the end will be something like, this movie is good, brilliant, good, amazing, blah, blah, blah. So it's not going to be really realistic text that is generated by the model. It just hacks the reward to go higher. So what is the remedy for this? What you do is that you create another copy of the generator, that you keep it the same throughout the training. So you do not update this model. It will remain the same throughout the training. And what you do is that you look at the generations of the generator model. So you look at the trajectories that are created by the generator, and you compare the probability distribution of the tokens of the trajectories versus the base model. And you punish the generation if it diverges too far from the probability distributions of the base model. So basically, in essence, what you are saying here is that I want my text to be still consistent with the model that I started with. So it wants to create text that is realistic and natural, but also have high reward. So that's the idea of the KL divergence. We add this as a term to the loss, and we put a coefficient in front of it to control the strength of it. If the KL divergence here that we have is super strong, so if you leave it at 0.5 or some high number, the model that essentially doesn't train that much. it will remain very similar to the base model that you started with. So for us that we are looking at sentiment analysis, it will generate both positive and negative sentiment completions. If it is very weak, it is likely that you will create a model that does reward hacking. So you have to find the right balance. For us, for this problem, this 0.01 works very well. Now let's take a look at the data preparation section. This section is not that important. Feel free to change it according to your liking. In fact, I have also borrowed some sections of it from the TRL library, but it's just you want to format the data in a way that you can give it to the data loader later and get batches. It's not that important. So here I first create a prompt data. Well, I first create the tokenizer, and then I create a prompt data set which creates the prompts of the IMDb form. We know that, for example, we use the hyperparameter of 30, so it will create 30 by batch size of prompts that are given to the generator for completion. And this is the data generator version of it. Feel free to go ahead and take a look at it. Nothing really important is going on here. And finally, I'm looking at the PPORL element. Essentially, these are the rollout elements. The rollout, one element of a rollout, and a batch of rollout, and then the storage rollout that we put all of these batches into it. Each rollout contains the trajectory together with the values of the logit and advantage estimations and all the other quantities that we need for the trajectories. These are all explained in the previous lectures. This is just a specific form of it that is appropriate for the language models. So I'm not going to go into the details of it. It's not that important. Just prepares the data in appropriate fashion. Okay, now let's take a look at the model architecture, which is an interesting concept here. So remember that our agent, our RL agent, is an LLM. So an LLM that generates text is an RL agent for us. And also remember that from the discussion at the beginning of this section, we said that we need two versions of the model. The base model, which we use for KL divergence calculations, so that the new model doesn't diverge from the natural text. And the other one that we call the generator. The main difference between the two models is that the base model doesn't need to be trained, so it's frozen. And secondly, it doesn't need to have a value head because it doesn't need to approximate rewards into the future. If you don't remember what the value head was, please go ahead and take a look at the previous lectures and see what's the meaning of that. Okay, now let's go back to the calculation here. So what we do is that we first create a model based on the path that we give it. So if it's not trainable, meaning that it's a base model, we freeze it. Otherwise, not only we don't freeze it, but also we add a value head on top of it so that it can have a prediction to the reward into the future. Also, since we have changed the model architecture, we have to redefine the generate function and also the forward function. The only difference between the forward function for the base model and the generator is that the base model doesn't have a value head. Okay, so that's the model architecture. Note that it can be pretty, the way that we defined it here is pretty generic. So you are not stuck with OPT. You can pretty much use any of the Hugging Face models, or you can even define your own model architecture. Okay, next, let's take a look at the reward model. We already had a discussion of how to train a reward model at the beginning of this lecture. So here we just call that model that we have already trained. Also, we do device map auto so that it's sharded into your compute machines. And then there's no training of the reward model here. So we set it to evaluation mode. Finally, we want to get a list of trajectories, or in this case, the trajectories are just sentences and paragraphs. We want to get a list of them and then spit out a list of the reward values or reward scores for those sequences. So we just do we tokenize the samples and then we give them to the reward, mount them into the device, and then there is also appropriate temperature for that, and then we will get back the scores. So nothing complicated is happening here. It's just a reward model that we trained at the beginning of this lecture. Okay, next let's go over rollout creation. So we first initialize our rollout creator, and this is the important function, make experience. So what we do here is that we create a list that contains all of the rollouts. We will use this to create a data loader later. So while the number of rollout hasn't reached, we just go ahead and create a new set of prompts from the custom prompt generator that we created before. So we create a new batch of prompts and we give the batches to the model, to the generator model, to create the full trajectories. The trajectories are the queries together with the responses. Now that we have the trajectories, note that this trajectory behaves very similar to the trajectories that we had in the previous lectures for the RL that plays games. So in this case, it's a sequence of tokens, but you can think about it as like a sequence of actions that has like probabilities and rewards attached to it. So it's very similar concept, but it's different in the language domain. So what we do here is that after we create the trajectories, now we want to see what are the probability distribution over these tokens. So we give it to the model and the reference model. Note that the model is the generator and the reference model is the base model. Probably a bad naming here, but with that mapping, you should be able to follow the code. So now we get the logits, so the probability distribution over the tokens that are generated, together with the values that the model expects for the future rewards. So the rest of the calculation is quite similar to what we had before for the way that we deal with the trajectories and the values. And also here what we do is that we just ignore the trajectories after either the end is reached or the stop token is reached. So and then we will go over the reward calculation. It is quite similar to the reward calculation that we had before, except that there is this complexity of the KL divergence here. So basically what we want to calculate here is the reward, but not just the reward, but also the difference that these values have, these sequence has with the distribution that the base model created. So remember, we don't want to diverge a lot from the probabilities of the base model. The explanation, the detailed explanation of why we use the KL divergence and how it works, the theory behind it, is explained in equation 2 of the Instruct GPT paper. So please feel free to go ahead and take a look at that for more detail. But really, what you need to know is that at high level, what we do here is that we calculate the rewards, the per token rewards, but what we do is that we modulate it and we correct it according to closeness of these tokens to the distribution that we have from the base model. So we don't want to diverge too much from it. After these calculations are done, we now insert all of them to a rollout element that we defined before, and then we put them all together into a batch, and finally we will add it to the all rollouts list. At the end, where we're done, we also take a look at the scores just to keep track of the progress. Note that this doesn't have any effect on the training. This is just to see how the model is training, and this is basically for tracking and logging. So then we will return all of the rollouts, which are a list of batches of rollouts. Okay, we're almost there. Let's take a look at the inference before alignment. So we create a reference model or the base model, and the model, which is the generator, the main model here. And I give the generator model these two prompts that the model is supposed to complete. This is an action Western, and the model is supposed to complete it. And the second one is I saw this movie recently because, and the model is supposed to complete it. So let's see how it does before alignment. So for the first one, it says this is an action Western. It's got a great cast and some good actors, but the movie doesn't have much to offer besides this. And blah, blah, blah. So the score, the reward score for this review, it seems that it's not very high. It's 0.1. Okay, a very low sentiment score. So the second one, it says that I saw this movie recently because I live in the area where it was filmed. Okay, interesting completion. So you can read the rest of it, and it completes it and it gets the score of 0.6. So slightly above average, slightly more on the positive side of things. Okay, so these are the completion. These are two samples of completion before the model is aligned. And in fact, if you go over many more samples, you see that the average score hovers around 0.5. So it sometimes creates reviews with positive sentiment, sometimes create reviews with negative sentiment, and sometimes in between. Now let's go over the training loop. Okay, finally, let's go over the training loop. We first download the IMDb dataset, and then we create a prompt dataset out of it. We create a storage that will store the rollouts and the rollout creator. We use, as an optimizer, we use the AdamW optimizer with the learning rate that we specified at the beginning. The rest of the items are for logging and progress. So remember, the training of PPO has two phases. The phase one is the rollout creation, that we create trajectories together with all the quantities that we need to store, such as advantages, rewards, and logits. So we go ahead and create all of those quantities, and then we store them in a train loader that we can now call batches from it. In phase 2, which we actually train the model. So in phase 2, we go over the data loader and get batches, and then we calculate the loss and then do the optimizer backward. So pretty standard and simple. Of course, we know that the loss function here is very involved, but as soon as you calculate the loss, the rest of it is pretty simple. Okay, now let's see how it goes with the training. So now I'm looking at the scores along the training. At the beginning, the scores start around 0.5, which is average, right? Close to 0 is going to be negative sentiment, close to 1 is going to be positive sentiment, and at the beginning we're somewhere in between. Sometimes we create negative, sometimes we create positives, and sometimes something in between. So at the beginning is around 0.5. And as we train the model, the rewards get better and better. So the model learns how to create reviews with positive sentiment. And until it gets to around 0.96, which is very close to 1. So at the end, it learns how to create sequences for the reviews which have a very positive sentiment. Next, we're going to look at the inference after alignment. We're going to use the same samples that we used before training, and we want to see what is the effect after training. So I give the same samples to the model, same prompts to the model for completion, and I look at the completion. So it says, this is an action Western. It's very well done with a great soundtrack and excellent performance, blah, blah, blah. And at the end, we see that the score is actually very high. It's close to 1. The other one, I saw this movie recently because I like the storyline. It is one of my favorite movies ever, and it has been for a long time. This was an excellent film with all kinds of good special effects that are very unique in this genre, blah, blah, blah. And you see that also the second one gets a very good score. Okay, so it means that we have successfully aligned the model with our artificial but easy to understand axis, which was sentiment. Finally, some words about the future of RLHF. Pre-trained models are capable of reasoning, and they have a lot of knowledge, but they don't behave the way we want them to behave unless we teach them. SFT works, but it's a passive method. Data created in SFT is not considering the model generations. So RLHF remains a critical piece in the future of Gen AI. Also note that RLHF is not limited to language. It can be used in any generative application where you can collect human feedback. For example, it is already used in text-to-image generation where it can significantly improve the quality of the models. Here you can see some examples on the left before alignment and some examples on the right where the researchers from Berkeley and Google used RLHF to fine-tune the model. And you can see that the precision is a lot higher. So it can be used for any generative applications. We can expect simpler versions of RLHF to emerge soon. I hope this mini-series was helpful for you to understand RLHF better. If it was helpful for you, please don't forget to support the channel. Thank you all, and see you soon.